Hello everyone and welcome back to your YouTube channel. As you must be aware, some of my students, they are creating some test system from scratch. That is an amazing activity because they can learn a lot how to use the excellent PowerFactory, and then they will have the capability to do more complex things, okay? This is very important inside your learning experience. But some of my students, they have been a bit, let's say, confused about the two winding transformer. When we are using three-phase transformers, and there is a delta star or star delta connection, there is a possibility of having a phase displacement, a phase angle between the voltages at the low voltage side and the high voltage side. What I trying to say is delta star transformers or star delta transformers, they allow to play with the connections, and using those connections we can establish some phase angles that can be identified between primary and secondary. And if you look into the IEEE C57 12.80, there is a definition of angular displacement. Okay, what is the angular displacement in a transformer? It's a very basic. It's a very basic definition. It's the phase angle expressed in degrees between the line to neutral voltage of the reference identified high voltage terminal and the line to neutral voltage of the corresponding identified low voltage side. Okay, the first thing that you must be aware is every single transformer has all the terminals with a clear label, very well identified. And as you must remember, if we are using the classical standard IEEE ANSI, H represent the high voltage terminals and X represent the low voltage terminal. Okay, every single three-phase transformer has these kind of labels: H for high voltage, X for low voltage. Okay, I am talking about the classical IEEE standard. Okay, the C57. And then, if you remember, this is the classical star connection. You have the terminals over here, and 1, 2, and 3, they represent the windings. Okay. Okay, here at the right hand side, you can see the three-phase phasor diagram. And as you can see, they are a three-phase representation where 120 degree, they are located between A, B, and B and C, and C and A. However, we can play with the connection of the windings inside the transformer, and when we play with the connection, we can create several phase angles. Depending of the terminals that we are connecting inside the transformer, we can create several phase angles that they will change between the primary and the secondary. Okay, what I'm trying to explain is, in this delta star connection, we can create some phase shifting between the high voltage and low voltage side. For instance, here we have the classical delta star 11. Delta star 11 is extremely simple to understand. On the right hand side, you can see this is the star connection. This is the low voltage side of this three-phase transformer. And on the left hand side, you can see here the phasor diagram. This is the three-phase phasor diagram for the delta connection, the high voltage side. Okay, here is the proper connection of every single winding inside the transformer. And finally, and more important, this is the location for the classical vector group representation using the clock. You can imagine this like the classical clock. Here we have 0 or 12 o'clock, 1, 2, 3, 4, 5, 6, 7, blah, 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 okay? Every single of these sectors represent 30 degrees, okay? What I will do is something very simple. As you can see here, this is the high voltage side, and this is the location for the voltage A to N. And in blue color here, we have the location for A to N, but this is the start connection or low voltage side. When we combine together, we have a phasor diagram that then I will rotate in order to make the voltage A, the high voltage side, to be at 12 o'clock. As you can see over here, the high voltage side is located at 12 o'clock, and at 30 degree or 11 o'clock, you can see the vector representing the low voltage side. And that is the reason that this connection received the name Delta Star 11. Delta Star 11 because the high voltage side is located at 0, and you can see that the low voltage side vector phasor is located at 11. And in this case, there are two ways to understand this. We can say that the secondary or low voltage side is leading by 30 degrees to the high voltage side, or the other way around is to say that the secondary or low voltage side is lagging by 330. You can use one of those expressions, but what you need to understand is that there is 30 degrees between the high and low voltage side, and in this case, the location for this low voltage side is at 11 when the high voltage side is at 12. Similar situation can be used to explain the connection star delta 11. Star delta 11, as you must remember, star is the high voltage side. You can see here the connectivity of all windings. And here you can see the connectivity for the low voltage side, the delta connection, okay? In this case, the delta connection in this case is creating what we call two phasors diagram here at the top. Well, again, what I am doing is creating the phasor diagram, including the high voltage side and the low voltage side. And then I rotate the phasor diagram in order that the high voltage phasor is located at 12 o'clock. And of course, when we rotate the phasor diagram, here you can see the location for the low voltage side or the secondary side of this transformer. And as you can see over here, is located at 30 degree leading the high voltage side, okay? And again, this is something very simple. What you need to understand is that the location of the high voltage side always should be at 12 o'clock. And depending of this number, 11, 3, 6, or any number here, it will be the location inside this clock. And in this case, the low voltage side is located at 11. And as a consequence, there is a phase angle of 30 degrees. But now the interesting question for my student is, how do we implement this inside PowerFactory? Okay, let's do that. Well, right now we are here inside PowerFactory, and what I will do is just basic things initially, okay? This is a simplified model that is at the system. The original system is a generic 12-bus test system for wind power integration. It was published in a conference paper of the IEEE. And the original paper is a collaboration between the Aalborg University and Vestas. Okay. However, this is the modified version of that test system. Okay. What I will do initially is I will run a load flow. Yes, and you can see we have results over here, but I would like to show you a bit more. I will go here into details and I will show you the vector groups. And also I will show you the power flow directions of active power using these arrows, okay? And right now, as you can see over here, for the generator number 1, the transformer is showing you the vector group, okay, the connection. Where is located this connection? Okay, if you remember, you can double click the component, and in this case, this is the transformer 1.9, and this is the transformer element, okay? The connections and the electrical parameters for the transformer is located inside what we call the type, okay? What we are doing now is going inside the transformer, and as you can see over here, you can define the different type of connection and also the vector group, okay? In this case, this is a transformer and the vector group is high voltage is connected in a star connection and the low voltage is a delta connection, okay? What I will do now is I will close and I can show you this bus bar is 15 kV, 15.5 kV, and this is the 230 nominal voltage of this bus bar, okay? And as you can see, delta is located on the low voltage side and start is located at the high voltage side, okay? Because I want my student to understand the meaning or the importance of phasor diagram, what I will do is I will create a small phasor diagram to show you the location of the phasor for the voltage at bus bar 1 and bus bar 9, okay? That is extremely simple. Just click here, create a new page. I will say this is a plot, and this will be phasors. I will plot the phasors V1 and V9, okay? Now we have here a graphic object, and I will create a new, let me go here, vectors, vector plot, okay? I will select vector plot, and right now what I need to tell you is that we want to select, let's see here inside the bus bar, I will select the bus bar number 1, okay? And then I will select, I would like to show you the magnitude of the voltage, and it's using phasor including the phase angle, okay? Voila, we have here the location. Let me see, this is V1. Let me go to my load flow, 0.99 and minus 4.1. And this is the location for the first phasor. And let me add one more phasor because we want to add also vector for voltage number 1. And right now we have here 1 at 0 degree, and that is the voltage of bus bar number 9. And as you can see, bus bar number 1 is a minus 4.1. And as you can see over here, this is the location. Right now we have the beautiful phasor diagram, and what I will do is, okay, let me show you here the phasor diagram. That is what I will do now. And to do that, what I will do is unlock the system, and I will say include. And right now I have a beautiful phasor diagram showing me the location of the voltage at bus bar number 9 and the voltage bus bar number 1. And as you can see over here, the location is minus 4.1, okay? What I will do now is I would like to show my students what is the effect of having the connection changed using the vector group, okay? What I will do now is I will go here and then inside the object type, and right now I will use a connection that is called, as you can see over here, Ynd11, okay? If I do so, let me run the load flow. And right now, as you can see, there is a bigger phase angle. If you remember, the original position was minus 4.1, and right now there is a phase angle, a bus bar number 1, 0.99. And the reason is that right now we add 30 degrees between the low voltage and the high voltage, okay? At this moment, if we consider the high voltage side as reference, we add 30 degree here, and that is the reason that we are having minus 34.15 degrees. As you can see, the effect of having the phase shift here is adding 30 degree because we are using the connection based on the YND11, okay? And I can show you in another way, okay? Let me come back the transformer to 0, okay? Right now we are using a star delta 0, and I will run the load flow, and as you can see, the phasor is located at minus 4.1, okay? That is the location. What I will do is I will use the comparison button, yeah? I will say, yes, it's okay. Let me use the comparison button. And right now I will change the vector group, and I will include the phase shift of 11. And right now I will run again the load flow, and voila, the difference is 11 is minus 30 degree. The difference is minus 30 degree, or if we want to use percentages, that is 735%, okay? I prefer to show you the degrees because otherwise you will be confused. But as you can see over here, the difference is 30 degree, okay? Let me do the following. Let me stop the comparison, okay? And right now we have, you can see here, delta on the low voltage side and a star on the high voltage side, okay? What I'm telling you is, let me put here, if we are using NYN, the angle result was minus 4.1. But now, if we are using, let me check here. No, it was, sorry. It was D0, okay? And now we have the angle is minus 34.1, okay? Now let's do the following. Let me swap here the connection, and what I will do is going into here, and I am changing the connection, and right now is And now the phase angle is still minus 34.1, okay? As you can see, I changed the location. Let me use the same. As you can see, I swapped the connection delta star and star delta, and the phase angle is still minus 34.1. What is the reason? Because the location 11 at the clock that is defining the vector group is still 30 degrees. Remember that the vector groups are defined considering the high voltage as a reference, and 11 is the location for 30 degree. That is the reason that swapping or changing here the location will give you the same result. Of course, in real life, swapping those connections and making those changes, they have very important impact on your power system. For instance, for short circuit, for faults, for asymmetrical faults, the location of the neutral point is extremely important. For that reason, I am telling you that from the load flow point of view, there is no issue changing the connection, but later for short circuit analysis, you will realize that there is a huge impact when you change the connection, when you swap the connection of this transformer, okay? Well, this short video, it was only to tell you that you can change here the vector group. You can define the vector group and you can define the connections, but it's very important that you understand what is the impact of them into the final power flow solution. Well, that is all for this video. Thank you very much for watching. Bye now.